Here we go. Hi, everybody, and welcome to the Fast Code Seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy. I co-chair the organizing committee for the seminar, and I lead community outreach for the larger Fast Code project, of which this seminar is a part. Before Roberto introduces our speaker, I'd like to take a minute just to let you know about the Fast Code seminar and the larger Fast Code project. You can learn about Fast Code by going to our website. I'm going to paste the link into the chat. And I'm going to share my screen. So now I think everybody's looking at the Fast Code website as I'm sharing my screen. And it's all about advancing software performance engineering as an open source community. If you scroll down the homepage, you can see a couple featured events. One of them just happened. That was a special workshop at P-pop. And you can also see the Fast Code seminar listed here. And Jan, of course, is giving today's talk. And we have a couple more speakers already scheduled as we head into 2026. Laxman Dhulipala from Maryland and Google is speaking in March, and Peter Sanders in April. If you have someone who you think would be a great speaker, please let us know. You can see previous seminars, many of them recorded. And you can also see our wonderful organizing committee, which includes Kuba Lackey, Roberto, who's here hosting, Christian Schultz, who might be in the audience, Julian Chan, and Yihan Sun. In addition to the Fast Code seminar, there's lots of things happening in Fast Code. And one thing I'd like to bring your attention to is we have a Fast Code blog. This is to help people learn about software performance engineering, even when they're not experts, get interested in what's happening. And we recently had a post that I just want to bring your attention to because it's fantastic and it's written by a new contributor to Fast Code, Marco D'Antonio, who's a PhD student. And he wrote about his work on accelerating the single source shortest path with priority aware work stealing. So I'm not going to talk about that right now, but I just want to say if you know someone or maybe yourself who's got work that you think would be great to popularize for a wider audience, we would love to help. So please let us know. That's all I have to say about Fast Code for now. I'm going to turn it over to Roberto to introduce Young.
All right, thanks, Bruce. So I'm really happy to introduce Jan Wassenberg. He's a senior software engineer at Google DeepMind. Got his PhD in 2011 from KIT, from the Karlsruhe Institute of Technology, and he has been helping the community releasing open source libraries that have a significant impact on the way we write code. Couple that I'm sure is going to talk about is Highway, which is the library for C++ library for portable intrinsics. So if you share the pain of rewriting code on different platforms, especially when that code does complex stuff, then you should know the benefit of this library and is the leading Gemma right now, which is the LLM inference library for CPUs at Google. Now, if you Google Jan, it's going to show up Google Scholar. You click on Google Scholar and you see that he has a 1500 citation for one paper published in 2025. And you said you were interested to see what's the title of that paper. And it turns out is Gemini 2.5. Jan was an author of that paper, at least listed as an author. Along with other 3,000 others in that paper, but still a pretty significant contribution for the world, for the community, and for the world. I'll stop talking. Thanks, Jan, for joining our seminar series, and the floor is all yours.
Thanks, Roberto. Thanks, Bruce, for organizing, and good to see some of you again after Dachstuhl. So I will power through a bunch of stuff. Hopefully we'll leave some time for questions, but let's jump right in. The contents here, it's basically a grab bag. We start with why and then look at how. So many of us know why we're here, but for those who are questioning, SIMD means huge constant factor speedups, something like 16 or 32 operations per instruction. We routinely actually see 10 times speedups from not even that much work. So why do we like it? Because it runs everywhere. It is easy to integrate in your systems and software, and it works basically across the entire CPU range. You're not tied to any vendor. Now, what do we use it for? Starting with the obvious ones, linear algebra, of course, everything is ML these days, but it gets a little bit less obvious the further we go, and there's also strings, cryptography, database, and even computational biology, including compression. So why are we here? Why are we talking about highway? What is that? We don't like to write the same code multiple times, as Roberto said. That's too expensive. And what highway is a thin abstraction over intrinsics. That means if you're starting with intrinsics, you already have them. It's pretty mechanically easy to port over from that. And it's actually helpful to get off of intrinsics because we can help you, because we're a wrapper. We can take care of the compiler bugs that unfortunately bite us on basically a quarterly basis. And compared with alternatives, we are predictable and relatively reliable in terms of the performance you can expect. Finally, highway is unique. I believe it's the only way actually you can target the newer ISAs RISC-V and SVE natively with their variable vectors. So let's look at the alternatives. If you auto-vectorize, which just means writing your C++ and trusting that the compiler will provide, it might look good, but the snowflake might also melt the first time you update your compiler. And it has blessed us with the worst code I have ever seen in my life. At the bottom here, that's a mem copy, 1 byte at a time. Some people, the true believers, still write assembly. Hats off to them. I believe FFmpeg is still holding up that flag. The thing is, if you forget one little prefix, the letter V there, it's a disastrous performance hit. And of course, it's super laborious to write everything, not just per platform, but per CPU family. And you have all this manual work to do, so not very ergonomic. And recently, SIMD was finally standardized after something like 9 years. And they have nice operator overloading, means the code is relatively readable. But the things you can do with it is very, very limited, unfortunately. And there's no runtime dispatch, no variable length vectors. As far as I know, it works best on GCC and ARM, maybe in the x86. Or we can do the hard work of using the intrinsics ourselves. So many projects do this. Unfortunately, it's error prone. And it's pretty verbose, actually. Look at the intrinsic on the bottom, just to load a vector. And unfortunately, there's also quite big differences between just two x86 variations. It's completely different operation here in the middle. So compiler bugs. I used to keep a list. I've stopped once the slide got full. They unfortunately regularly hit us. It's very difficult to test compilers on real-world code. Highway has managed to work around most of these, except Clang 6. We threw the towel on that. We simply require Clang 7. So what was Highway again? It's mostly header-only library that wraps the intrinsics and provides polyfills or emulation for operations that a certain CPU might not have. And we've been open source since about 5 years now. I'm appreciating the input and advice we got from many people outside of Google. And it's quite widely used now. I was surprised to see today there's something like 69,000 Git clones of this library. And with thanks to 99 contributors, and it's basically available everywhere in package managers, Linux, and Microsoft, Conan, and so on. Recently, there was also a master's thesis which found that Highway was the best option that they investigated. So what is it actually doing under the hood? You have here an op called if vec then else. And there's an optimized implementation which calls a specific intrinsic here, plus some type wrapping
Jan,
magic.
we have a question from Chris. What do you mean by best?
Well, according to the criteria that they had, how easy to use is it, and how performant on the various platforms. And let me see, what's the title of this master's thesis? I'll paste it into the chat. Thanks for the question. Okay, so
Great.
We have this specialized intrinsic, we have type wrappers, and we have a generic implementation. But you don't really have to know that. You just have to know that there's single operation which has this documented effect and it works everywhere. And your code looks like this, which is more or less standard C++, a little bit of a C tinge. And so you're in a loop, you're loading mull and store to square an array. And maybe the one interesting thing here is the loop increment is a variable. It's a highway function that tells you how many lanes or vector elements you processed in a loop. We'll talk more about that later. So very quickly, there are a couple big users of Highway. And we started off actually with and for JPEG XL. And it had to work with both server and mobile. We couldn't afford to handwrite for all the platforms. So the 9 engineers on that shaped and informed the Highway API. That worked out nicely. And there's some image processing things besides the compression. We'll look at a small example later. And my main project right now, also a big Highway user, is gemma.cpp. That's LM inference. You can think of it as llama CPP, but simpler. You only write it once, not 7 times. And last time I checked, it's also considerably faster on workstations. So this is a platform that we use to test and develop new inference algorithms. Previously, I've also done other SIMD-related things, VQ sort, highway hash, and there's actually a port of this by an external contributor that is implemented in terms of highway. Whereas random, that's the secure random generator, that's the default at Google that is using cryptography, but not quite the highway itself. It's an earlier version. There's a bunch of other users, some big projects that you'll recognize, Chrome, TensorFlow, V8, and a couple of dozen open source projects.
Jan, we have a question.
Question.
Yeah, from Tim. The C++ standards folks are working on a standard C++ interface for vectorization. And how does Highway compare to that?
They are working on it. They have been working on it for 9 years. Unfortunately, the design from that time was predating some of the CPU changes. So it's very difficult for them to support variable length vectors with this design. And unfortunately, it lacks a bunch of features I would consider essential. That said, I am aware that they have been discussing adding new ops to increase from the 50 or so that they have, sometimes referring to highway, which is good to see. And perhaps that will change with time. Does that answer the question?
Tim, you want to? Yes, he says.
Excellent. Thank you.
Thanks, Jan.
So let's imagine importing. First, we will have some kind of type magic. We will declare upfront we're going to be working with, let's say, vectors of floats. Let's also say we're going to have ints alongside of them. Let's say also we're going to have doubles and we're going to cast between them. So the first green section here, that's just empty tag types. And this struct SIMD we see here on top. And what Highway is doing conceptually is simply providing overloaded functions that take various of these tags and return then a platform-specific type from them. In your user code on the bottom, this is actually creating data, whereas the first green text was only types. The second ones are actual vectors, which you get out of these factory functions, 0 and set, or iota returns a sequence. So first you declare the tags, then you get your vectors. And then if you look at a diff here, this was some simple loop from JPEG XL. We're going to replace the loop increment, of course, and every array access. So instead of individual elements, you're going to deal with tuples or vectors now. And the vector is loaded with load, of course. C++ calls it a copy from and copy to for some reason. Since the 70s, every single CPU calls it load and store, but okay. Then we also we are able to fuse plus and then times into a mul add up. But in general, it's simple. You just simply have tuples, and you're going to load and store them in a loop. Now, here we have a little bit more complex example. It's a bit and random generator, XOR shift. So we're going to see how to implement that integer code. So again, we have the type thing on top. We have a loop. We load. Here's a little wrinkle. We don't recommend that you use overloaded operators. The compiler support is not quite there. Hence, we use a shift left function. And as usual, load and store then to the memory. Questions so far from the porting? Feel free, and I'll continue in the meantime. Cookbook takes us to various small little topics which are practically relevant when we use SIMD. So there is a little hardware detail that leaks out to us. Hardware likes it when vectors are aligned. That means the address of the vector is a multiple of its size. So Highway tries to nudge you to make sure of this in that the default load function crashes or is allowed to crash if it's not aligned. You can use load U for unaligned, but we recommend that you ensure either with stack allocated arrays with this Highway align or with the dynamic memory allocator that we provide. So if your vectors are aligned, several small performance potholes will not hit you. And next, it's quite common, unfortunately, still that we have arrays of structures. That means a point with two different fields. Generally, SIMD works best when each vector element is its own thing. They're all x's or all y's. So if you're able to ensure that up front, great, that's the best thing. But second best is Highway actually provides ops that reasonably performantly load those x and y and separate them into all the x's, all the y's. Next, branches. We are not GPUs. We don't have per element divergence. Every SIMD operation does the same thing, pretty much. So how do we do what would have been a branch? We use the ternary operator, which in C is the question mark operator. So what that's called in the Highway is if then else, or a variance if then else 0, or if then 0 else. And instead of returning a bool, we don't have really the concept of a bool because you have a tuple. What should we say? The tuple is greater than or equal to 0. We want all of the tuple to be greater than or equal to 0. So the way we check this, simply checking that the absolute value is equal to the original value, and that is true of all of the vector elements. So what we have here, by the way, and yes, I use the overloaded operator. We shouldn't do that. What we have is that the comparison operator returns a mask, which is a special type. And this mask has its own op, for example, all true, which then returns a scalar built-in bool. So that's how to avoid or replace branches. Next, we'll again emphasize the point that there are a bunch of strange and wild and wonderful ops that are far beyond simple plus, minus, and equal, less than. So Highway provides a bunch of them, about 400 at last count. And we'll look at a couple of them now. This reorder, widen, mull, accumulate is, funnily enough, it's relaxing the invariant of this operation by allowing reordering. That means you don't know in which order the elements are returned. That's fine in many cases, including the very interesting one of a dot product. You don't care what the order of the elements is, only that the sum is correct. And this is what we get here. And the funny thing is that gemma.cpp, the matmul, is basically built around this op. And it's super efficient for BF16 number types on all the CPUs today, basically. Then there's another one that SVE encourages this kind of code, but it's actually efficiently implementable anywhere, even without special instructions. That BF16 types, we can take every even or every odd lane and promote them to float, and then do FMA. Then we have a funny construction, which is a fused version of two operations, an XOR and an AND NOT. Or 3 actually even. This is a single instruction on x86 SVE power, and otherwise we'll just emulate it as best we can. So this is a good example of Highway choosing carefully the set of operations that we can implement efficiently everywhere, but also taking advantage of the specific ISA-specific instructions wherever they are available. Another such example is you can take a mask, such as is every value equal to 0 or something like that. And compressing, that means you compact the vector elements so that only the ones for whom the mask is true will be kept or moved into the lower lanes of the vector. That's useful, for example, during sorting to partition. And finally, we have very often a table lookup instruction. This is super important and very widely used, and actually quite powerful, that you can actually gang together two vectors and then do an arbitrary element-wise index into these two vectors. And that is very efficient on most platforms, and for those it's not, we'll reasonably emulate it too. Okay, that's a whirlwind tour of some of the more exotic Highway instructions. Any questions again? We'll take a moment. Yes, question.
There was a comment from Christoph. Do you want to unmute and just share that comment?
What I wanted to say is that the explanation of the tags might be helpful for new people for Highway. Like all of those, how to those scalable tags, etc., etc.
Okay, yeah, thank you. Good point. Let's take some time to dive more deeply into this. So this is a very common pain point when we have workshops. The first confusing point for people has been distinguishing between the tags and the vectors themselves. So again, the tags don't have any data, whereas the vectors don't have any type sometimes. Right. So usually the most common case is we're going to deal with a full vector. We'll call this a scalable tag. That means however big the vector is going to be, we just want 100% of it. Then it is possible to say, for example, half is a template, and that with a tag argument, it returns a tag with half as many lanes. So there's a concept of a half vector. And why is that important? Because when we promote or demote, usually we return one full vector. That means when we promote to a full vector, the input argument is half a vector. So the way we make this work is we say we rebind or we repartition. Rebind, the terminology is from C++ allocators. What this means is we're going to keep the same number of lanes, but we're going to change the type of the lane from float to a signed integer. Conversely, repartition means we're going to keep the same number of bytes, but we're going to chop up the vector into a differing number of lanes of this new type. For example, we start off with a df float tag as the argument. We're going to change it to double. That means we have half as many double elements of twice the size. So again, you would use that when you promote or demote to vectors of different size. Thanks for the question. I think that covers it. Anything else? Good. So one of the more advanced topics is we saw a simple loop. That's clear enough, but it assumes that it's divisible by the vector size. Unfortunately, that's not always true. So the first thing we might use, or the first attempt we had, was, okay, many ISAs allow masking or predication. This is pretty convenient. We have an op that returns a mask with the given number of bits set. Then we can simply mask load and, for example, compress blended store. That means we compress, as mentioned, keep only the elements where the mask is true. And then we store. Blended store means we're going to overwrite that memory with a full vector. But unfortunately, there's a fly in the ointment. We found out later, unfortunately, that AMD, the manual reserves the right to fault. That means they're allowed to crash even if your mask is false if you cross the end of a page. And that unfortunately greatly limits the usefulness. It doesn't actually crash if the vectors are aligned, which is anyway a good idea, but it's not so wonderful. So we introduced a second different operation. That's load n. That means load up to one vector of the specified count. So that means if you have the remaining number in your loop, we're going to load, let's say, 3 elements. And on a masked ISA, that includes AVX512, SV, RISC-V, basically the modern ones. And there, this is equivalent or as fast as the masked previous op. But on other platforms, it's going to safely but somewhat slowly do the right thing. That means there's branching there. But in general, I think it's generally good practice to have a main loop where you have no predication, simply loading full vectors, and then one copy of the main loop to handle the remainders. And that one last iteration will use then this load and store n. And the way the main loop then looks is a little bit counterintuitive. Rather than simply continuing until I is less than count, what we're going to do is check that it's at least one full vector, and then stop at the last full vector, bolded here. And the reason we do this is GCC likes to emit static analysis warnings otherwise. So this structure guarantees and helps the compiler understand that there will not be any overflow. Good. So that's the topic of the loop remainders, which is quite a pain. Now we come to variable length vectors, which is actually one of the cornerstones of why Highway is designed as it is. So what does this mean? First of all, what is even a variable length vector? Why do we do that? So the encoding space of ARM, the ISA, is quite limited. They decided that they don't want to have, like Intel did, they don't want to have 128, 256, 512 instructions. They want to have a scalable vector extension, SVE, that implements some vector size, and you don't know what that size is at compile time.
Jan, we
That
have a
means
question. Sorry to interrupt. Tim, do you want to just ask this? Unmute yourself, please.
Oh, sure. This could have been asked at any time. So I hate to interrupt this as well, but I'll just say it that I'm very impressed by Highway, but I'm a C programmer, not a C++ programmer. So there are lots and lots of concepts here that are going to take me a while to absorb, and I'm not going to get from your talk, and I'm not going to get from your slides because they're not self-contained. So I'm just wondering, do you folks involved with the Highway project have clear documentation at a tutorial level to explain this online as a PDF, not videos, as something I can properly study? I haven't poked around to see what you have online for written documentation.
Yeah, that's a good point, and unfortunately a pain point. We do have a quick reference style that's similar to the ISM manuals that, for example, the ARM or x86 intrinsics provide. That's a short summary only of the op. That does not get you what you're asking. What we do have is a fairly lengthy README and design rationale of Highway. So that will get you pretty far, but it's not quite a tutorial, unfortunately.
Yeah, that's right. Okay, that's a problem. Okay, well, then thank you very much. If I'm going to use Highway, I need to create that tutorial. So, all right.
This could be a fast code initiative.
That's fair. I could imagine collaborating on something like that. Also, it could be interesting to ask your favorite LLM to generate such a thing.
I would not do that as a matter of principle, but that's another problem. That's my problem.
Okay.
I don't learn it if the LLM generates it. If I generate it, I learn it. So that's why. But that's my own
That makes
problem.
sense. That makes sense. It can be useful to help you also learn or ask questions to help the understanding.
Right. Understood.
Okay.
Thank you.
So we were at, yeah, thanks for the point. That's unfortunately something we should build. So we were at the sizeless types, and we have that. The ISA says my vectors might be 128 or they might be 248 bits. So what that means is at the compiler level, the compiler does not know what is the size of that type. That means it can't be a member, it can't be an array, and several other things. Unfortunately, the standard SIMD interface is entirely built around the concept that vectors are going to reside in a class. It kind of makes sense, but unfortunately, it's a complete no-go for this design. So fortunately, Highway has a way around that. We have the tags that separate the vector bits from the type, actually. Still, on some platforms, the vectors are classes. They're strongly typed, but on the platforms where you have sizeless types, it actually works. So the main surprise here is that this lanes function, the vector size, is not const expr. So not known at compile time. Now we've discussed some workarounds. Can we just say, oh, we're going to have vectors sit on the stack? Maybe that's okay for SVE. For RISC-V, that can actually be 64,000 elements. That's maybe not a good idea. So we recommend dynamically allocating using the functions provided. Now, if you don't know how long is a vector, then certain operations become more difficult. A loop, as we've mentioned, even with the remainders, is quite simple. But how do we transpose? So what we did, this should read 1 by 4, by the way, sorry. What we do here is use a special op that's, as mentioned, for the structure of arrays, that we can store every fourth element to a different position. And that basically gets you a 1 by 4 transpose. And we have one more somewhat wild use case that's from the quicksort, which involves a sorting network, actually of quite large size. Whereas the standard library quicksort has a sorting network of 357, something like that, elements. This is more like 256. So the way that works, even if you don't know how big or how many elements your vectors have, is you actually use a runtime if. This is not as crazy as it sounds. It's actually bearable because it's only logarithmic many branches. And on platforms that actually do have compile time known vector sizes, this code goes away, boils off into nothing. So to summarize, to transpose, you can use the special ops, and otherwise, sometimes, unfortunately, you have to special case each possible vector length. But these cases are rare. Now we come to runtime dispatch. What does that mean? That means when Chrome, for example, is running, you don't know, is it SC2? Are you running on ARM? Are you running on SVE? So you want to compile your code for multiple targets and then choose at runtime the best possible one that the CPU supports. So first, some terminology, but the main thing we want to know is just what a target is. That's a list of the sets of instruction sets that Highway supports. For example, we combine AES and AVX2 into a so-called AVX2 target. Now we're going to compile your code multiple times, once for each target, and specialize your same code then for that target. How does this work? We promise that you're only going to write your implementation once. That's here in the middle of the slide, the not green text. So this is really write once, but it's compiled many times. And how do we do that? And we don't have to change the build system. Don't worry, it works for any build system, CMake, Meson, whatever. The way we do this is just a little bit crazy. But it's actually reasonable and works well. We have a for each target header, and this header is going to include your source code multiple times. So what is actually being compiled is basically the glued together version of several copies of your code with different configuration for each target. Now, how does this work? Surely if you copy paste your code, you get ODR violations because you're repeating your function. Nope. We're going to put your code in a namespace, which is changing in every compilation pass. That means the highway underscore namespace changes for each target. And to make this work, you require something like 10-20 lines of boilerplate, and here are most of them. So you have to tell what is your file name so that we can include it. And you have to say the things that you only want to compile once. For example, the call into your various implementations, that should be compiled exactly once and at the end of the file. So for that, we have a highway once. And this is maybe the craziest thing. People rapidly understand the tags, but the fact that your code is being compiled multiple times, that's the biggest stretch for people to wrap their heads around. But this is quite solid, stable, and shipping in very many projects. And I think this is, unfortunately, as good as we can do in C++. So there is a little bit of boilerplate again that we call into your various functions. So recall that your
Jan,
implementations are... Sure.
There's a question. Do we need different backend for different platforms, or are there magic insights that work in hardware agnostic manner?
Thanks for the question. So typically we compile several targets, but for the same ISO. That means when you ship an x86 binary, it's going to contain AVX2, AVX512, SC4, and so on. When you compile for ARM, you're going to get a FAT binary, which, for example, supports SVE and Neon. So although your code is portable and each one works well on that particular platform, Highway does not have any mechanism to make the, for example, x86 instructions run on ARM. What you have to know is what ISA, or what, let's say, general platform family your binary is for, but this is quite standard practice. For example, when you download something, some package, then you typically say, oh, I'm on x86. The advantage we have is that this x86 binary contains all the different code paths for example, AVX 512, and we choose that at runtime. So dispatching means, since we had multiple namespaces, we're going to call a function from one of the namespaces. How do we know which one? We generate a table of function pointers, that's this highway export, and we're going to call into that table. Static dispatch means I know there's just a single target, I've only built for one. Dynamic dispatch means actually choose the best available from that table. Now, here's a little explanation why we have these funny before namespace and namespace things. So as mentioned, the highway namespace changes in each compilation pass, and that's what prevents multiple copies of my func from basically colliding. Second, the compiler requires us to have certain attributes on this function. The attributes saying I'm allowed to use, for example, AVX2 intrinsics. You can put highway attra in front of each function. That works. It's just a little bit error prone. But even better is if you say highway before namespace. This is another pothole. There was a compiler that crashed if we did this in the namespace. Hence, the name reminds you to do it before the namespace. So what this before namespace does is it ensures that all the functions inside the namespace are going to get this attribute. So all you have to know is you have, in exactly this order, the before namespace, your namespace, the highway namespace, then your function. Then you don't require this highway attra. So what this gets you is you're allowing the compiler to generate the code for that target as desired. Now, sometimes you want some header shared between multiple files. You think this is going to break because a header usually has an include guard that by design, the second time you include that thing, it's going to stop that file from having any effect. But that's not what we want with this multiple include pass. However, there is a magic include pass-like thing that does what we want. In fact, a colleague helped me come up with this, this approach, and it's that every time you include something, you alternate between a 2-bit state. Should I include it or should I not? And the definedness of a macro is that 1-bit state. So highway internally flips this macro, and this include guard ensures your code is included exactly once per target. And one even crazier thing, if you would like to not dynamically dispatch, but simply forward declare something, what we would need to do is forward declare for each namespace that highway is going to basically create. So your user code does not know which namespaces that could be. So how do you do it? You pass to a highway this macro saying, for each namespace, I want you to do this. And that macro content then forward declares here, as you see. And you call a highway visit targets, which will cause it to forward declare then for each target. What this means is you can simply call a function defined in some other translation unit without the overhead of a dispatch. So let's recap the question.
Yes, related to the previous question, is it possible to compile for a specific CPU model and hence get a slim binary instead of a fat one? And if yes, do you observe noticeable performance differences?
Yes, good question. So highway is very flexible. You can bypass this runtime dispatch. You can compile for exactly one CPU or target. You can select a subset of targets that you care about. For example, if you know that your code involves predication, then it's probably helpful to include more targets. If you know that it's anyway limited to 128-bit and memory bound, then it doesn't even make sense to have wider SIMD. So it can absolutely make sense to say, oh, I'm only going to compile once for SC4 and that's it. So we provide macros that say disable these instruction sets or don't even compile them. And there's also a configuration macro in the highway that says compile only one, the best available, depending on the flags that I've passed to the compiler. So that takes us back to here, this terminology. And baseline is the flags that you give the compiler, so MAVX2. So the static target is the best baseline that is actually available. And the again, you have full control. The default is to build all of the attainable targets. That means everything that Highway knows about, then you'll get that. What you can do is cut that down by disabling specific ones or saying I'm only going to compile for this static target. Yep, welcome. Okay, so let's recap here what this runtime dispatch is doing. We have some macro magic, which, by the way, is optional. You don't have to use it, but I do think that runtime dispatch is very important for many distribution cases, browser, app store, things like this. So your code is compiled only once. You generate a function table, and then you call into that table. There are some highway users that say, I'm a supercomputer. I know exactly what hardware I'm running. I'm going to compile only for one target. The fun thing is it's exactly the same code except for these green things. So if you don't want the dynamic dispatch, simply skip that. The rest can stay, the before namespace, after namespace, all that stays. Just don't, for each target, just don't export in dynamic dispatch. Okay, that is our whirlwind tour of the advanced features of Highway, and I'm happy to answer more questions.
Thank you, Jan. Any questions? Any other question? So I can start with one. Unless I missed something, you haven't talked much about debugging. Any complications with the code repetitions and that comes out if I want to know if a thread is doing something and a thread is doing something else, and maybe there are two threads doing the same function, just named in a different way. Any like debugging related issues or features that you have embedded?
Yeah, that's a great question. So I'm happy to share my current practice. And funnily, it starts with we have an internal code review tool, which is very, very good at spotting mistakes in the code. The funny thing is I'm finding that this is almost the fastest way to find bugs, even before we actually debug. But the first thing I usually do is run the sanitizers that the compiler provides. ASAN, MSAN, TSAN in that order. So this tells me if something is exceeding the bounds of an array or use after free or this kind of thing, or if some memory is uninitialized. Mm-hmm. And the next step I would do is then step by step look at each element and how it compares to scalar code. So this is a really important principle that you never write vector code directly. You always first write the scalar thing, and you have a test that compares them. And this will very likely find the bug.
Awesome. Tim is asking a question. What about C? Yeah, Bruce, you can go ahead.
Great. Jan, in your response to Roberto, you talked about an internal code review tool. So for those of us who are not in Google, does that help us at all? Or can you just elaborate on the internal tool and what it means for us?
Yeah, unfortunately, that's not more widely helpful. I'm just not familiar with the external state of the art, what agentic IDEs are providing.
There are a few. There are existing tools I can help.
Mm-hmm. So we've got Tim's question. Tim, do you want to just unmute and ask your question, please?
Sure. So I'm very fond of dinosaurs. It's a passion of mine. And I'm one of those in that I write C. I'm trying to get comfortable with the C++ world, but it's bizarre and weird and all that stuff. But I'm just really curious. Highway is tightly coupled to C++, which is great, but doesn't Google care about C code? There's an awful lot of legacy C code out there, and people keep telling me Rust is going to take over the world. So it really comes down to a more general question. What is your thinking about vectorization and writing this kind of code across languages?
That's a great question. I know of several other programming languages, including Rust and Go, that have considered basically a highway for Go, a highway for Rust. For Rust, I'm aware that until recently, or possibly still, they had compiler limitations which make that difficult. And unfortunately, the design of the SIMD in Rust has went down a different path. They've decided to let you say, oh, my vector is going to have exactly 16 elements, and let the hardware then struggle to make that happen. So, of course, that interoperates really poorly with the concept of the hardware is telling you, no, my vectors are actually 4 elements. So the compiler has a really difficult task there. I do understand that there are some efforts also to bring variable length vectors to Rust. And I know a colleague is actually working on this together with the Rust compiler team. So what I think would happen, what I would hope happens, is that the highway concept and the set of operators that we've developed, and of course all the polyfills, that would be transferable with whatever syntax that Rust requires. I'm not familiar enough with the details of the Rust macros and the way they have let's say the equivalent of C++ attributes, how that is implemented within Rust. So I wouldn't be the one to implement that, but I'm also happy to talk with anyone who is involved with that. I think you also asked about C and do we care about it?
I was about to say, Jan happily skipped the C part.
I noticed that.
So yeah, I've also written C. There is something nice to the simplicity. The highway concept is very, very strongly in need of a type system stronger than C's. So it is quite important for us to have templates. Otherwise, it's simply impossible to do what we've done. And what would be required is like OpenGL style, that everything has suffixes that you're going to not load, but load f half or whatever. And that would, I think, explode in complexity. So I'm not sure I would
believe
recommend
me,
that.
I understand that. The thing is, in the community I come from in scientific computing, there's a vast, vast, vast amount of legacy C code that is not going to go away in my lifetime. So it greatly limits the applicability of highway in the high performance computing domain.
Yeah, that's
fine
fair.
because
that does make sense.
Because I completely understand your answer. I mean, I'm involved with complex libraries, and what we have to do between the C and the C++ implementations is a nightmare. So yeah, I understand. Templates are wonderful.
Yeah, I believe you. So the good news is you can compile mostly, if it's well written, C code as C++, and you can dip your toe in, right? It is quite possible, and to have an example here, I don't think so, but it is possible for this caller function that can actually be C callable, this one. So you could compile the implementation of this highway using code with C++ and have it exported or called by C code that only sees this caller function. That would, I think, be a decent path.
Yeah.
If we're ready for another question, there is one from Benson. Benson, do you want to unmute and ask your question? I can ask Benson's question. Do you also compare accuracy across different hardware platforms?
So the accuracy will only be relevant for a floating point. Everything else is exact. And there are two classes of errors. There is so-called approximate functions, which are platform specific in how approximate they are. So anything called approximate is a warning signal that this is going to differ. And the other thing is contractions. So FMA and the order of the floating point operations. So even within a platform, the compiler can differ in how it compiles this thing and with what flags. So this we are unable to say anything really meaningful about. In my experience, the FMA difference is something like 10 to the minus 5. And this is somewhat similar to the loss that you get, for example, from rounding to BF16. So my advice would be that tests should include some epsilon tolerance, both relative and absolute, and should be written for floating point code to expect that you're going to have differences and should tolerate that. Then it's robust to both the compiler changing and the hardware changing, in that you either get FMA or don't.
Thank you.
We're getting close to the top of the hour. Before we run out of time, I want to just remember that Tim a while back asked about tutorial style material for the highway, and I sensed like some possible future work there. I want to invite anybody who's interested in that. Would you please click the raise your hand on Zoom, and just take a second to raise your hand if you're interested in that. And if anyone's interested in sort of talking more about that, please reach out to me at on the fast code community, and I would love to follow up with both Jan and Tim or anyone else who's interested in having a tutorial for Highway. Jan, did you want to add anything to that?
Just to thank you for that excellent idea. And yes, I'd be happy to work with people.
Fantastic. I see that not everybody has a raise a hand option. So just please, if you're interested, send me a note. Any last questions? We are at the top of the hour.
There's a couple of other questions on the chat. Oh, no. Okay, sorry. There was a comment about Rust.
I see a question. Will we be emailed the recording? We're not emailing the recording, but we are going to post it. So the same place where the talk was announced on the Fast Code site will be the recording, and that'll be by tomorrow. Same place where the other recordings are listed for the previous talks.
Well, I think that's it. Jan, that was great. Thank you very much. And thank you everybody for attending the talk.
Thank you, Roberto and Bruce, for organizing. Thanks all for joining. And happy SIMD writing help you get good speedups.
All right.
Thanks, everybody. That adjourns our Fast Code seminar. See you next time.
Thank you, Bruce.